Okay, YouTube, this is my first video in which I'm exploring quadratic functions, and we'll move on to models. But what quadratic functions are, and we're already familiar with the fact that, in terms of families of functions, we say quadratic functions are any functions that are in the same family as this basic parent function right here, where we have a squared x term if it's a function in x. So the highest degree of any term is 2, and that's what gives it away that it is a quadratic function. So let's go ahead and look at a definition here. We say let a, b, and c be some real numbers, and we're not going to allow a to be 0, but we say the function given by f of x equals ax squared plus bx plus c is called a quadratic function. And again, what gives it away that it's a quadratic function is that this is a polynomial, and the highest degree on any term is a second degree thing. So basically, it fits in the same family as these, and we get these parabolic graphs like the ones you see over here on the right. So really quickly, quick note here, we do not allow a to be 0 because consider the consequences of allowing a to be equal to 0. If it were, then this term wouldn't exist in the first place, and then we would have just some linear thing, mx plus b or bx plus c in this case. So looking to the right here, let's go ahead and point one thing out before we begin anything else. We often prefer to write quadratic functions in what we call a standard form, okay? So this ax squared plus bx plus c thing, we could transform its equation into what we call standard form. And sometimes you will hear this referred to as vertex form, okay? So if you hear vertex form or standard form, we mean the same thing, but we call it vertex form because essentially it's going to tell us where the vertex is. So the note that I want to make here is this. When we consider the parent quadratic function, that is this f of x equals x squared, if we were to make a table of values, we would see that 0 squared would be 0. If you plug in 1, we get 1, 1 here because 1 squared is 1. And if we plug in 2, we would get 2 comma 4 because 2 squared is 4. And then we know that this is an even function here, so it has symmetry about the y-axis. So we get some function that is u-like and is centered around the origin. And as we deviate away from these x values around the origin, it has a slope that gets steeper and steeper. So knowing this parent function right here, we say that this one here has its vertex at 0, 0. But more generally speaking, we could say that if we give this in standard form now, we write it this way. We'd say a times x minus h squared plus k, where a is not equal to 0. So the thing I want to note here is this. When you look at this form here, what we know is that this h is responsible for left and right shift, okay, or horizontal translations. We know that this k is responsible for up and down shift, so vertical translations. And I will make another note here. We'd say that this h value is backwards, okay? Now the reason why I say it's backwards is because, well, when you look at the formula, we have a negative here, okay? And because we have a negative there, if h is equal to a positive 2, say for instance, you would have something that says, minus a positive 2. It's kind of hard to see here. It would look like that, which when you simplify it, looks like x minus 2. So when your eyes see that, you're going to say, well, that's a negative 2, but in reality, it's a positive 2. Whereas if we were to make this, say, a negative 2 in here, if we were to take away a negative 2, that'd be the same thing as adding a positive 2, and it's going to look like x plus 2 even though the value of h is negative. So just recalling that this value of h here is backwards, so if it says minus 2, it actually shifts right 2. If it says, positive 2, it shifts left 2. So that being said, we call this vertex form because if we have a function that typically starts at 0, 0, if I were to say I'm translating it h units left and right and k units up and down, then I will always be shifting this vertex point away from the origin, h units left and right, k units up and down, and it'll be located at h comma k. So important things to mention here, at least with standard form, we say that the vertex is always located at h comma k, and you'll notice that that's what's illustrated here in this diagram, h comma k. Also this, we know that all parabolic functions in x, either open, up, or down, they have this axis of symmetry that runs through the middle. Or at least I'm going to point this out to you. We refer to this as the axis of symmetry. So just to abbreviate it for you, I often write it as AOS. But the axis of symmetry is always a vertical line. And I can tell you this, it always has the equation x equals h. We know that vertical lines have x equals some constant. And why x equals h? Well, it's symmetric about a vertical line that runs through its vertex, and I know that the vertex x value is always h, so our axis of symmetry equation must always pass through that same x value. So we have an equation that is x equals h, okay? So the only questions I want to kind of write some notes on here is this. We say, well, what if a is positive? What if a is negative? If a is positive, then we have something here where we have a normal transformation of our parent function, which always opens up, the parent function does. So we say if a is positive, it implies that it opens upward, okay? And if a is negative, that's that transformation of a function where we see this, occurring, that would cause it to reflect over the x-axis by making your y values negative. Okay, so this would open downward. So this opens downward. So I just want everybody to see here, I kind of made an exploration tool in Desmos, but I've typed in this f of x equals a times the quantity x minus h plus k, where we can modify the a, h, and k values. But going back to what we just said here, looking for our a values, we can see that if a gets bigger and bigger, it's just stretching our parabolic arc. So instead of going up one, right one, which would be our parent function's typical path here, up one, right one if a is equal to 1, let's say I take it times 5, well then what's going to occur is that it's going to go up 5, right 1. It'll be vertically stretched away from there. And if this is a number a between 0 and 1, we're going to have vertical shrink. If I make it a half, instead of going up 1, right 1, it'll go up a half, right 1, okay? That being said, also we said if a is negative, this is where we're getting reflections over the x-axis. So that a value directly tells you where this first point will lie with respect to where the vertex is. And then as far as h and k are concerned, if I make h, a positive 3, then it's going to go right 3. Now keep in mind that if you put a positive 3 up here in this formula, it's going to look like x minus a positive 3, which looks like x minus 3. But that's horizontal translation. So, we could see that our vertex here would be at 3, 0. Our values for h and k are 3, 0. If I were to now mess with k, say make k 1, you can see how that directly corresponds to this vertex value h and k. So now that we've established that we have vertex form here, h and k will be our vertex value, and then we say that the axis of symmetry is the line x equals h. We also know that a is positive, it opens upward. If a is negative, it opens downward. What we're going to confront is what we do if this is not written in standard form. So we know that oftentimes with quadratic things, we define them like this. Okay, we say f of x is equal to this. So our goal in this next step here will be able to rewrite this into standard form by completing a process that we call completing the square. That's what we'll talk about in the next video. Cheers.